Hello everyone. Hello. We are on the fifth day of our Dotnetos week, slowly ending it, but we have super nice presentation for you, and we invited Stephen Toub today to talk about .NET performance because he is a .NET performance guru. So who's better to talk about .NET performance? So just a few words from me because we would like to listen Stephen, not me. So Dotnetos Week is an initiative provided for you because we have some partners. Thanks to our partners, which is a KMD company and Demand Technology Center. So very many big thanks to those two companies for supporting us, for providing you all those talks, in fact. And as I said, this is a Dotnetos week, so we had 5 presentations. I can say we had because now this is a fifth presentation on Friday. We had different speakers that you can see. We had Melanie, Martin, we had discussion panel, and Sebastian, all about .NET stuff and let's say pretty performance related and low level stuff. So if you haven't seen those presentations, feel invited to watch all of them because they are really awesome. And to do that, you can subscribe to our channel so you will be notified about all the stuff that we provide, we present, and we plan to present in future to not miss anything. So really, please feel invited to subscribe and to not miss anything important. And having said all that, it is now the best time just to close my mouth and just give a voice to Stephen. One more thing, I will invite you to ask questions because you have Stephen Toub online, so there is a very nice occasion to ask anything about .NET performance. Ask questions on chat. I will gather all those questions and we will ask Stephen all those questions in the end to not interrupt him during the talk. But do not hesitate to ask everything. And say hello to Stephen on the chat also, from where, for example, you are listening to us. So having said all that, just removing my slides, adding Stephen. Hello, Stephen. Hello.
Hello.
And I'm closing my video and giving you the whole control. So have a nice talk, and I'm listening also.
Great. Well, thanks very much, Conrad, for the nice intro. So my name is Stephen Toub. I do work at Microsoft on the .NET team. My job isn't specifically about performance, but it's one of the things that I really love about what I do, and one of the things that makes me excited to go to work every day is ensuring that anyone in the world who's using .NET, their applications, their services, they just continually get better and better and faster. And so a lot of what I do is guided by that. There have been a huge number of improvements for performance for a lot of aspects, for reliability, for new functionality, new APIs, and performance that have gone into .NET 5. There is, and this isn't the first time that's happened. If you look back at previous .NET Core releases, you'll see that performance is a really big theme. And in fact, I've really enjoyed sort of towards the end of every .NET Core release, taking the opportunity to sort of summarize a lot of the improvements that have gone into the release from a performance perspective in blog posts. So I wrote a post about .NET Core 2.0, 2.1, 3.0, and a few months back about 5.0. And I remember feeling pretty much at the end of every post, wow, I wrote a lot, but I have no idea how I'm going to write the next one, because how could we possibly do better than this? And then the next release comes along, and my post ends up being even longer than the previous one, because part of it is I ramble, and part of it is there's just so much goodness that goes into it from the .NET community at large, whether from folks at Microsoft or in the community, to improve the performance of the whole stack. It's really incredible. So .NET 5 in particular has seen just staggering gains across the board. There's no way that I can talk about all of it in an hour talk. There's no way I could even write about all of it in a really long blog post, even though the post I was referring to, it covered something like 250 PRs that contributed to improved performance of the stack. So what I plan to do is sort of three things. One, briefly talk about things that we've done in .NET 5 to help developers change their code to take it to improve its performance using functionality that's already available in this and previous releases of .NET. One is a little bit on new APIs that have been added in .NET 5, since in every release we're adding lots and lots of APIs, lots and lots of methods types, etc. And some of them are always about improving performance. So I want to talk a little bit about that. But then I want to spend the rest of the talk sort of doing a survey of some example performance improvements from across the stack and the kind of impact that they can have on your applications. So let's start with sort of this idea of discovering opportunities for better perf with .NET 5. One of the things that came about in the C# compiler multiple releases ago was this idea of being able to plug in custom analysis code into the compiler in the form of what are called Roslyn analyzers. And these analyzers are able to examine all the code that's being compiled and then issue suggestions and warnings and errors about that code, and then even provide fixers that are able to transform the code from its initial state into the desired state. And over multiple releases, there have been a lot of analyzers written inside of Microsoft, outside of Microsoft, as part of officially supported packages, as part of a plethora of other analyzer packages. And you can just go and use these in your applications just by pulling them down from NuGet. But we haven't in a long time shipped static analysis in the platform itself. And one of the things we've done in .NET 5 is bring in a large number of analyzers that are in the box, and many of which are on by default in one way, shape, or form. Some of them by default to just issue additional warnings and errors as part of any compilation. Some of them will show up as suggestions in Visual Studio. Many of them have fixers associated with them. And we've implemented a bunch of new analysis rules in this release as well. Some of them focused on correctness, where we're able to detect things that are almost certainly bugs in the program, and then other things that are suggestions for improving things like performance. So I have one example here. This is a little trivial application written to compile on .NET Framework or .NET Core. So there's some APIs that I'm using here that I wouldn't otherwise use on .NET Core, but I'm using this so as written, it can compile on either. And all it's doing is it's creating two sockets that are connected to each other, wrapping them in streams, and then doing a ping pong between the client and server. The client sends some data, the server receives that data, sends it back to the client reads it. And it does that about 10,000 times. And then it does that whole thing just repeatedly, each time printing out how long it took to execute those 10,000 ping pongs and how much memory was allocated along the way. So I can take this code as is. I can compile it and run it on .NET Framework 4.8. And on my machine, I get results like this. So these 10,000 ping pongs end up taking about 0.57 seconds and allocating quite a bit of memory, allocating about 18 megabytes of memory as part of this. Without any changes, I just recompile and rerun this code on .NET 5. And I get results like this. So about 0.49, seconds, so about 10% faster, 15% faster, but using way less allocation, which in the grand scheme of an application can then have kind of multiplicative effects and cause the whole application to run faster, because other allocations won't end up producing as much impact on the garbage collector. So we dropped from about 18 megabytes down to about 1 megabyte with no code changes. But now I've got my code. It's running with .NET 5. I'm in Visual Studio, and I got a little suggestion that pops up that says, hey, I see you're using stream.readAsync, passing in your array, your int, your offset, and your count. FYI, there's this new overload you might want to consider using, and oh, I can change it for you. And there's another overload of readAsync on stream that accepts, instead of an array, an int, and an int, it accepts a memory of a byte. And instead of returning a task event, it returns a value task event. That value task is beneficial for a few reasons. Well, first, the memory is beneficial for a few reasons. One is that you can actually create a memory that tells the system the underlying data is already pinned, which then avoids the implementation having to repin, allocate GC handles and stuff like that. So there's a potential cost savings there. But from an allocation perspective, the fact that we're returning a value task means that if the operation completes synchronously, which is very common when reading from a stream, because you're getting data that there's a good chance is already available, we don't have to allocate the task to return. So there's a memory savings there. But on top of that, we've optimized socket and network stream and some other streams in the implementation in the core libraries to actually even avoid the allocation when it completes asynchronously. Because of how value task is built, we're able to pool some allocations under the covers. So I apply this fix across my program, just hit fix all occurrences. I compile and I run, and now the time is about the same, but memory is literally 0. So we dropped from 18 megabytes with .NET Framework to about 1.5 megabytes or a megabyte with .NET 5 with no code changes. And then we apply these fixes and all of a sudden we're just in a much better place. So we've tried to add a bunch of these kinds of analyzers in the box, and we plan on doing more in the future. We'd love to hear from you on the kinds of analyzers you'd like to see as well, and also have you contribute some ideas and implementations of your own too. All right, so just a brief look at the kinds of things where we're trying to help people and developers better take advantage of functionality that's already available to them. Then there's new APIs, right? In any release of .NET Core, there are dozens or hundreds of new APIs that are added across the stack for any number of purposes, for functionality, for correctness, for performance. There are way more APIs than I can talk about here, but I just want to highlight a few to give you a sense of the kinds of APIs we're talking about. And in particular, one of my goals anytime we add new APIs to the core platform is that we also utilize those APIs in the core platform. There are millions upon millions of lines of code that make up the core core.NET libraries, whether in .NET Core app itself in the .NET Core shared framework, or in ASP.NET Core and its shared framework, or in other areas of the stack. And in order to validate the design of APIs, it's really helpful to assume that if we're shipping these APIs for others to consume, there's a really good chance we should be consuming them as well. And so as part of the same PR that add new APIs, or soon thereafter, we're really keen on using those new APIs in existing ones. And that means that in addition to you as a developer using .NET being able to use these new APIs and change your code to improve it and make it run faster, it also means that the very presence of those APIs and their use in existing ones means your application just gets faster without any code changes on your behalf too. So just a few examples of that. Since the beginning of .NET, you've been able to say new array, new int square bracket 42 close square bracket to allocate an array of 42 ints, for example. And when you do that, the runtime provides various guarantees about what it's doing. And one of those guarantees is that it's zeroing out the entire contents of that array. It's ensuring that it's all zeros across the board. Whether it's a value type or a reference type, it's cleared out. And in the case of reference types, or in the case of value types that contain references, the runtime does need to clear that state, because it needs to ensure that the references are either, that any references are either 0 or they point to something valid that the GC can traverse. But for anything else, for integers, for bytes, for chars, for value types that wrap other primitives, technically there's no reason that it has to be zeroed out. And so one of the APIs that's been introduced in .NET 5 is this GC allocate uninitialized array method, which is exactly the same as new int or new t, square brackets length, except it doesn't forcibly clear it out if it doesn't have to. And we now take advantage of this in types like string builder. So when string builder allocates its character arrays under the covers, it doesn't actually need to clear out those chars, because it's only going to use as much of the arrays as it's actually written. And so it doesn't need to pay the cost of that zeroing, of that clearing. These overloads also provide some additional functionality. You notice the second argument to this after the length is this optional pinned argument. And this is exposing some new GC behavior in .NET 5 that is a pinned object heap. So in addition to the other heaps that the GC employs, there's this new heap, the POH, or the pinned object heap, where it guarantees that any arrays that are allocated there won't be moved around. And that means that you can pass these off to native code through interop without actually pinning. I mentioned earlier with stream.readasync, if you pass a memory, you can create a memory that tells the system this data is already pinned. You don't need to create a GC handle for it. That works very well with this, where I can allocate these already pinned arrays and then just pass them through the system without having to worry about GC handles and the like. And you can see this being taken advantage of heavily in ASP.NET, in Kestrel, for example, where it's creating these giant, what it calls memory slabs of big arrays that it then uses, kind of hands out pieces of to various parts of the system. And whereas previously it would have to allocate and pin, or would have to use native allocation to get something that wouldn't move around, now it's able to create these pinned arrays. So pretty cool stuff. Another interesting example is this new skip locals init attribute. Yeah, as long as we're talking about zeroing, one of the things that the C# compiler does by default on pretty much any method that it compiles is it outputs this locals init directive in the IL, and that tells the runtime to clear out all of the state on the stack. Now the runtime would already clear out state that it has to. For example, if you have a reference on the stack, like you might get inside of a span, it has to clear that, again, to ensure that it's either 0 or a valid reference for the GC to traverse. But everything else is sort of an optional clearing that's done for some additional safety. And so by default, the C# compiler is pretty much always emitting this. If you were to look at the assemblies that we ship in previous releases of .NET Core, like .NET Core 3.1, you'll notice, though, that those directives don't exist. And that's because there's a cost to that zeroing. And in particular, there's a cost to that zeroing in functions that do a lot of stack alloc. So if you say stack alloc byte 1024, and you have that locals init directive, which you will pretty much always by default, the runtime has to clear 1K of data on the stack as part of entering that method. And we don't want to pay that overhead as part of the core implementations that we ship as part of the core libraries. So in previous releases, we would run a post-build processor, an IL rewriter, to remove all of those init directives from the core assemblies that we ship. But now in .NET 5, the C# compiler understands this new attribute, which you can put on a method, you can put on a type, you can put on your whole module. And this tells the C# compiler to not emit that directive to the runtime, at which point the runtime will only clear what it absolutely has to. And so for certain kinds of coding that are span heavy, using stack allocs, for example, this can make a very measurable difference on your code. So we use this now in every assembly that we ship as part of the core framework. Another example, a ton of work done on hardware intrinsics. In .NET Core 3.0, we exposed literally hundreds of new methods for x86, x64 intrinsics, meaning there are instructions that come as part of things like SSE2, SSE4, ABX2 that allow for some very specialized operations, in particular used as part of vectorizing code, to basically do multiple things at the same time. And these are now all exposed up as methods that can be consumed in C# applications, that allows C# to have access to those instructions directly. And then all of these instructions were used in a bunch of operations on types like string and span and UTF-8 encoding to make the operations go much faster when those instruction sets were available. What we didn't have in that release was similar ones for ARM. And so now in .NET 5, there are hundreds upon hundreds of new methods that are hardware intrinsics for ARM64. And then we've, again, plumbed those into similar places such that we now can light up on pretty much whatever instruction set you're targeting and have very fast support for operations like, searching or transforming strings or doing encoding and so on. You can obviously use these directly in your own applications if you want to, but they're also a real boon for the functionality in the platform itself. And then one more example. There's a task.whenAny is an example of an API we have in the framework that takes a params array. And for those who don't know, a params array basically allows the call site to pass any number of arguments, but have a single overload that accepts them. And it does this by taking an array, and the compiler under the covers allocates a new array to store all the arguments and then passes in that single array. So there's an overload of task.whenAny that takes a params array of tasks, so you can pass in 1, 2, 4, 100, however many tasks you want into this. But one of the things we did was, we're constantly looking at code that's using .NET in our own in our own repos, on GitHub in general, in customer applications where the customer shares them with us, or the community shares them with us. And one of the things we notice with task when any and other APIs that take params arrays is there's often a very finite number of arguments that are passed. And with when any, literally 99% of all call sites we saw had exactly 2 tasks, which means that not only were those call sites incurring an extra allocation for the array the compiler had to generate, but then under the covers, we had to make a defensive copy of that array because we need to use it after the call has already returned. And so we need to ensure that the caller doesn't call when any and then mutate it and muck with what the implementation is expecting to find. So we've exposed a new overload of when any that takes 2 tasks, and we can avoid both of those array allocations. You don't have to change your code at all. When you recompile, the compiler will just bind to this more specific overload, and you get the benefits of that. And this shows up again internally in the framework. It's used by HTTP client. It's used by Semaphore Slim. It's used by other places. So there are many more examples of this, but I just wanted to highlight a few of the kinds of things that we add in a release to help others write their code faster, make their code go faster. Okay, so leaving those 2 topics behind, we're going to spend the rest of the 40 minutes or so talking about how examples from where you can just upgrade your application from .NET Core 3.1 to .NET 5 and things just get better, which is something that makes me really happy at the end of the day. So again, just to reiterate, this is not in any way complete. I don't have time in 40 minutes to talk about the hundreds upon hundreds of changes that have gone into this release for perf. If you're interested in more, there's a blog post that covers a large number of them. It covers about 250 PRs, but even that is incomplete. I wrote it a few months ago, and it was not only incomplete at the time, but lots more improvements have come in the interim for .NET 5. But it should give you a really good taste of the kind of works that's been done. So let's dive in. I want to start with an interesting topic because it may be, I find it fascinating because it might be counterintuitive to some. And that is we spend a decent amount of time over the last few releases, including .NET 5, moving C and C++ code out of the runtime into C#. And one of the main motivating factors for this is sharing as much code as possible as we can between runtimes. If you look at .NET 5, it includes both the core CLR runtime and the mono runtime. And we want to avoid as much duplication as we can between them. And a great way to do that is to move as much code as we can into C# in the libraries that are shared across both. If you look at corelib, system private corelib, we do recompile it for core CLR and we do recompile it for mono, but about 95, 98%, some extremely high percentage of the code is exactly the same between the two. And the only parts that differ are those that have to deal with very specific aspects of the runtime. And so the more that we can move out of core CLR, for example, into C#, the more we can share that across both. So there's a sharing benefit, but it turns out there's actually a performance benefit as well in a variety of forms. One of them is that, well, C# in general is safer, is more secure than C and C++. And that's purely because of one of the main things that .NET provides, and that's it provides this managed environment that provides additional guarantees around your code. If I have a pointer in C or C++, and I walk it and I have an off by one error, I may end up reading or writing to memory that I didn't intend to. Whereas in .NET, if by default, if I'm just iterating through an array and I have an off by one error and I go off the end, I'm going to get an exception. And so the more code that we're able to move from C and C++ in the runtime to C#, the more this core code gets those additional kind of defense in depth measures, which we really like as .NET permeates more and more web services, infrastructure, applications, really important code out there in the world. But an interesting aspect of that as well is once we sort of have this code that is sort of safer in many ways, we're more willing to see changes made to it. We're more willing to see it churn. We're more willing to accept PRs to it and to accept them faster because there's less of a chance that such changes to really, really core code in the stack will end up introducing security vulnerabilities and the like. And because then more folks are able to contribute more faster and turn it around faster and experiment more, we actually see it often run faster, not because C# is faster than C or C++, but because just more effort went into finding minute optimizations or use better algorithms or the like. On top of all of that, there's then also benefits, just the fact that there is a cost to calling from managed code into the runtime. In many cases, we try and minimize these costs, and there are lots of tricks that are played to do so, but there is still a cost to it. And then there's also an aspect that has to do with GC that I'll get to in a moment. So let me just highlight an example of this. So in all previous releases of .NET, there was a native implementation for sorting built into the runtime in C that was used for sorting primitives. And if you were to call a method like array.sort, that, on an array of integers, for example, that would call into this native implementation in the runtime and try and use that. If it wasn't a primitive that could be sorted by that, it would come back out to managed code and use a managed implementation. But for this release in .NET 5, we moved that whole implementation out of native code, ported it to C#. It's almost all safe code, with the exception of a few really tight loops in a few places where we did end up using unsafe code to ensure that it could be as fast as we could possibly get it. But we were then able to scrutinize, those few lines that were unsafe to ensure that we weren't doing any buffer overflows or anything like that. Once this was in managed code, we're then able to leverage it in additional ways. So in addition to it being used for array sorting, we can also use it for sorting spans, which means now you can take data from pretty much anywhere, whether it's an array or some arbitrary memory of T that you received, or a native pointer and a length that you want to wrap into a span, and now you can use the sorting functionality. And in fact, array sort is actually now layered on top of the span sorting, as is system links enumerable.order by. So again, you can see us reusing this functionality ourselves in other areas of the stack. With this all in managed, though, we now get some additional benefits. Not only is it effectively as efficient as the native implementation, but we no longer have the costs of calling into the runtime, which shows up in particular for short arrays of 10 or 100 items, things like that. So here's a very simple, trivial example. I've got an array of 10 integers, 9 through 0 in descending order. And I'm just going to repeatedly sort it and then put it back into unsorted order and sort it, put it back into unsorted order, sort it, and see how fast this runs. We can see this is using benchmark.net. I just ran this yesterday on my machine, and we can see there was a nice jump from .NET Framework 4.8 to .NET Core 3.1 because of other optimizations that were done of about 20 or so %. But then going from .NET Core 3.1 to .NET 5, there's yet another 30 or so % on top of that, leading to a much more efficient implementation of sorting in .NET 5 than in .NET Core 3.1. Which is cool in and of itself, but there's actually another interesting benefit to this, and that has to do with pause times in the GC. So for certain kinds of garbage collections, the GC effectively has to pause the world. It has to kind of get all threads suspended into a state where it can then have a cohesive, consistent view of memory, understanding what's being used, what's not being used, and being able to move stuff around. And because of the tricks that are being played to call from managed code in our core libraries into the runtime, there aren't always all the checks and polling in place to allow the GC to efficiently pause some of these threads. It kind of has to wait for the code to get back to a place where it can pause it and then happen to notice that it can pause it there. And if it doesn't happen to catch it at that moment, it might have to wait again. We can see this with an example, this very simple program. It's spinning up a background thread that's just sitting in a tight loop calling array.sort over and over and over and over. So that's running off in the background. And then on the main thread, 10 times we're calling GC collect 15 milliseconds apart. And we're timing how long those 10 calls take, and then we're doing it over. And so what we expect to see output to the console is if we're sleeping for 150 milliseconds and we're making 10 calls to GC collect, it'll take a little bit of time. Let's effectively round it up. Let's say 200 milliseconds, we should see output per iteration of this. And I say GC collect shouldn't take much time because there's no allocation being done here. So there's nothing further for it to do. There's not a whole lot of memory for it to walk. It should be very fast. So we'd expect it to take around 200 milliseconds, waving my hands. But when we look at what it actually takes, I ran this on .NET Core 3.1. It produced very similar results on .NET Framework 4.8. Not only is it not 200 milliseconds, it's an order of magnitude slower. 2 seconds, 3 seconds, 4 seconds, 5 seconds in some cases. And that's because the GC is having a hard time getting that background thread to be paused so it can do the investigation it needs to do. By moving that array sort implementation into managed code, we've effectively allowed the GC to pause it pretty much whenever it wants to, effectively whenever it needs to. Again, there are other ways we could have done that. For example, inserting more polling positions into the native implementation, or changing the mechanism by which we call from managed code into native, but both of those would have added additional overhead as well. By moving it all into managed, not only do we get the efficient sorting we saw on the previous slide, but we get those pause times down to exactly what we expect them to be. So I run this on .NET 5, and now I see it's taking approximately 200 milliseconds, just as we sort of predicted it might. So there's some really nice benefits. This wasn't just limited to array.sort. If you look at a lot of the contributions that Jan Kotis made in the release, a bunch of them were moving pretty much all array processing and buffer processing out of the runtime and into managed code. So pretty cool. Okay, so a cool example with runtime. Let's move on to another aspect of the runtime, and that is the JIT, the just-in-time compiler. So the just-in-time compiler is the thing that's responsible for taking the IL generated by the C# compiler, for example, and translating that into the assembly instructions that the machine is actually able to execute. In addition to trying to maintain that functional correctness and the functional guarantees, it also is responsible for ensuring much of the security and safety guarantees that the .NET runtime provides. So, for example, it's responsible for inserting the bounds checks into array accesses and span accesses and string accesses that are there to ensure that if you happen to try and walk off the end of the string or array or span or whatever it may be, that you're going to get an exception. So one of the things, because this is so pervasive, because it would have to be inserting bounds checks on every array access, every string access, every span access, the JIT also goes to some pretty long lengths to try and remove the bounds checking when it doesn't actually need it. So for example, if you have a loop for I equals 0, I is less than array.length, I++, from the beginning to the end, inside the loop you do array sub I, the JIT can tell, well, you're not walking off the bottom because you're starting at 0. And it can see that you're not going to or beyond array.length by the very construction of the loop. And it sees that all you're accessing is that slot in the array, so it can eliminate the bounds check on that access. And there are a variety of other patterns that historically the JIT has been able to eliminate, and previous releases have added more and more cases where it's able to eliminate bounds checking. But especially now with how pervasive spans have been getting across .NET code, and how new patterns are emerging using span, there are other opportunities for the JIT to eliminate bounds checking in other cases. So let's take an example. So this function, try 2hex, is a little function that's taking an integer, 4 bytes, and each byte is 2 hex digits, and it's trying to write those 8 hex digits out to this output span of char. So it's checking to ensure that the span is at least 8 long. It's got a mapping from bytes to the corresponding hex digit, and then it's just indexing into the integer and doing the bit masking and shifting to grab the relevant nibble, translate it, and store it out into the output span. So a couple things to note here. The first is, for those of you that are paying really close attention, this new byte array might look really strange. I'm going to talk about performance. Why on earth would I be allocating a new byte array every time I call this function? Thankfully, I'm not. This is an optimization that's actually existed in the C# compiler for several years now. But for types like byte and bool and sbyte that are 1 byte long, the compiler is able to see, well, I see that you're allocating an array, but you're immediately storing it into a read-only span. You're not storing it anywhere else. You can't fish out that byte array from the span. Span doesn't allow that. And it's read-only, so you can't mutate it. There's no way using safe code that you would recognize that this is actually a byte array. And so the C# compiler doesn't actually generate an array allocation. Instead, it blitz the relevant data for this array into the binary. And then the instructions that it generates are actually just loading up the pointer to that data from the binary, loading up the length, creating a span using the span's pointer int constructor. And that's the span that I'm getting. And this is actually an incredibly fast way to use static data like this, faster than if I had allocated the array, stored it into some static singleton, and then used that inside the method. But this is relevant for another reason. This is exposing the length of this span in a way that the JIT can see it really well. And because the JIT knows the length of this span, it can use that for some additional bounds checking elimination. So we can see here, if I take a look at just one of these axes, there's actually two span axes here. There's writing into this span on the left, and there's reading from this span on the right. And actually, with optimizations that were added to the JIT in previous releases, it's able to eliminate this bounds check on the left. It's able to see that it was already proven that the span is at least long enough to access 0 through 7. And it can see with a constant index here that we're accessing 0 through 7, so it will skip emitting the bounds checks over here. But in .NET 3.1 and earlier, it doesn't omit, it emits the bounds check for map. So if we look at the assembly that's generated for .NET Core 3.1, we can just walk through it quickly. I've annotated it on the right here. We can see that this value shift right by 4 is this shift right instruction. Then there's this masking by 15, that's this AND instruction here. And then we have these two instructions here. This is in hex, so this is 16. And this is basically comparing the result of that shift and mask against 16, which is the length of the span that it was able to see up here. And then if it was outside of this bound, then it jumps to a location in the IL that you can't see here, or in the assembly, which you can't see here, which is going to throw an exception. Assuming it didn't throw, then it goes and it reads that value out of the map and it stores it into the resulting location. So when we talk about a bounds check, it's these two instructions here. Now, in .NET 5, because the JIT can see that it can tell that any possible masking by 0xf is going to be within the length of something that's 16, it now knows, hey, it can skip this bounds check entirely. And so if you look at the code generated in .NET 5, that just doesn't show up at all. And while two instructions for a branch rather, may not seem like a big deal, this one function is doing that 8 times. And given the nature of this function, it's pretty likely it's going to be used on some kind of hot path, doing a ton of formatting, being called many times. And so these two instructions can add up. And if we run this with benchmark.net, we can see not only was .NET Core 3.1 about 3 times as fast than .NET Framework 4.8, but .NET 5 is about 30% faster than .NET Core 3.1. And a large part of that is due to this kind of bounds check elimination, which if you look over an application can really add up in all the different places in the core libraries, but also code consuming the core libraries experiences. So that's one category of improvement. Another category of improvement that JIT does, lots of PRs get submitted for the JIT to recognize additional patterns, to recognize things that are important to the kinds of code that people are writing. And in particular, we often focus on things that are showing up in core types because those then end up having a very strong impact on the code using them. So let's take a little example here. Let's say I had code like this. I'm creating a new array of B, and B derives from A. I then try and create a new span of A using that array of B. Now, if this were a read-only span, this would actually be okay, because with a read-only span, I'm only going to be accessing these in a read-only fashion as A's, and B's are always A's, so that just works. But with a writable span, let's say I then got a reference into the first slot in the span. I have a reference as an A, and I try and assign a C to that. Well, C also derives by A, so from a C# perspective, this is okay. But from a runtime perspective, I'm storing a C into an array of B's, and that violates type safety. That would be really bad. So you can't do this. And you can't do this because the span constructor has this check in it. This check basically says, for value types, this doesn't matter because you can't have value types deriving from other value types. But for reference types, I need to make sure that the exact type of the array passed in matches an array of type T. If those are different, that means I was in this situation where I was trying to pass in a B array to something that was expecting an A array, and I need to disallow that. So if we benchmark this and we look at what this costs in with something like new span of string, like we don't actually, this check is there to protect us from bad stuff happening, but we don't want to pay anything for this check because 99.99% of the time it doesn't matter, right? It's indicative of an error in my program. So let's take something like a span of string, and I'm just passing in a string array. I run this. .NET Framework, we can see it was taking 27 nanoseconds. On .NET Core 3, much faster. It's about 4 times as fast, 3.5 times as fast at 8 nanoseconds. And then that cost basically evaporates with .NET 5. We can also see that if we look over at the code size over here. This is utilizing the disassembly diagnoser that comes with benchmark.net that allows you to see the assembly code and see how big the assembly code is. We can see the cost is basically gone. Why is that? Well, if we look at the assembly, I'm not going to walk through all of this, but certain things probably pop out. And in particular, if you look down here at the bottom, you can see that there is an assembly call to this throw array type mismatch exception helper that's up here. And if we look at the .NET 5 version, you notice it's nowhere to be found. And the reason for that is the JIT is now able to eliminate, in many situations, this entire piece. First is there was a change that was made to teach the JIT how to treat type of t.isValueType as a constant. The JIT knows whether t is a value type or a reference type when it's compiling this constructor. And so it can just turn this into a constant true or a constant false. And that allows that first part of this to go away. If it determines that it's a value type, then the whole thing goes away. If it determines that it's a reference type, then it still needs to evaluate the second piece. However, there was another optimization that was done that says if T is a sealed type, then there's no way that there could be no way we could be in that situation where we're saying we're expecting an A array, but we're getting a B array, because there's no way that B could derive from A. And as such, if T is sealed, it can also eliminate that second part, which means it can eliminate the entire check. And that's why for this string case, we don't see it showing up anymore over on the right-hand side, and it's running significantly faster. Again, really cool stuff. One last JIT change, because this one I think is really neat for a variety of reasons. We've talked about zeroing a couple times now in this talk. We talked about it with arrays. We talked about it with init locals. But there are places where we just can't get away from zeroing. For example, this is a silly little example. I don't know why you'd write code like this, but I did it to get a bunch of spans onto the stack. And span is basically a tuple of a ref and a length. And that means that this code ends up with a whole bunch of refs on the stack. Those refs need to either be 0 or they need to be a valid reference to something for the GC to traverse. And that means when the JIT generates the code for this method, in the prologue for the method, basically the code that's run when the method is called, the first thing that happens, it needs to zero out all the relevant state in the method. In the past, well, one of the changes that came in, actually from someone external to Microsoft, from Ben Adams, was to basically, rather than kind of zeroing out one at a time, it would vectorize that zeroing, take advantage of the XMM registers and SSE2 instructions to do that zeroing. And so if we look at the code that's generated for this in .NET Core 3.1, the relevant instruction here is this rep instruction. You'll see that popping up a lot in the prologues of methods. This instruction is basically a loop, a repetition. And that's that 28 times is going to start at the address in RDI, and it's going to write EAX to that. EAX here is being zeroed out. So basically this is going down. RDI is going to be decremented or incremented, whichever way you're going, each time. And so we're going to basically write 28 zeros as part of this rep instruction. In .NET Core 5, you notice there's a little bit more instructions here, but you'll notice all of these XMM and vector instructions. that are, there's still a loop, but rather than doing one at a time, it's doing multiple zeroings at a time. And that makes this run significantly faster. You can see in .NET Core 3.1, this zeroing benchmark was taking about 19.5 nanoseconds. And in .NET 5, it's taking about 16.5 nanoseconds. And that's largely due to this improvement in zeroing. And while this may not seem like a lot, this overhead actually was showing up in a whole bunch of methods that were making heavy use of spans in the runtime itself, in strings and encoding and wherever. And by making this change, we saw some significant improvements, 15, 20% improvements on some of the key benchmarks that we measure. So again, a really nice change and an example of one that didn't even come from someone at Microsoft, which I think is awesome. Okay, so moving on from the JIT. By the way, I was given permission to run a little longer than an hour, so I'm going to take advantage of that. Apologies if you were hoping this was just going to be 1 hour. I'll go a little bit long. So another thing that lots of applications use, obviously everything uses the JIT, but pretty much everything uses collections. And so, and one example of a collection that pretty much everything uses is dictionary. And so every release, we've had improvements go into the dictionary to improve various scenarios. And this release is no different. There have been a variety of PRs that have gone in to sort of streamline try-get value, taking advantage of ref locals and ref returns to avoid indexing into things multiple times or making unnecessary copies. There were changes to use more intricate math to do the modulo operation that we need to find the right bucket in the hash table faster. And there were changes that optimized for additional kinds of comparers. Previously, we would optimize for ordinal comparisons on string keys. Now we also optimize for ordinal ignore case comparisons on string keys. And you can see the impact of this with a really trivial benchmark that just calls try get value a bunch of times with different keys. You can see there was already kind of a 3x improvement going from .NET Framework to .NET Core 3.1. But then going to .NET 5, there's yet another 2x improvement on top of that. And with how much dictionaries are used and how much try-get value is used, this kind of change really adds up across the stack. Another example that pops up all over the place is text processing. And by text processing, I mean parsing like int.parse, or formatting like int.toString, or casing like toUpper, toLower, toUpper invariant, or searching with index of any, or encoding UTF-8, Latin 1, or ISO 8859.1, those sorts of operations. And again, in every release, we think we've hit the best we can do, and then someone finds yet more possible optimizations. So various examples of that. This was from someone external to .NET. They found ways to streamline int.toString even more by ensuring that from the public API, you could get to the core routine that was doing the real formatting much faster with better inlining, skipping a lot of intermediate steps and various overhead. You can see going from .NET Framework to 3.1, there was already more than a 2x improvement. And then going from 3.1 to 5, there's yet another 2x improvement. So again, with all the formatting that applications do, this kind of thing can add up. Or with encoding. So Levi Broderick on the .NET team, every release he ends up doing a whole bunch of work in encoding and finding ways to optimize things, whether it's by using better bit twiddling hacks or by streamlining accesses to things, or by optimizing for ASCII, whatever it may be. Some significant improvements that have come in for things like UTF-8 or ISO 8859, which is now in .NET 5 exposed publicly as the encoding.Latin 1 API. And you can see here, not only, again, were there significant improvements going from .NET Framework to .NET Core 3.1, there are yet additional significant improvements, upwards of 2x in some cases, going from .NET Core 3.1 to .NET 5. Really cool stuff. And another, searching as an example. I think this was another PR from Ben Adams, so from external to Microsoft, improving how the vectorization and optimizations inside of index of any are done, such that we get another 30% improvement going from .NET Core 3.1 to .NET 5 by using inside of index of any. Another example of text processing is regex. And I won't spend too much time talking about regex because I know that there was a talk earlier this week on regex and RDoS attacks. But I will spend a couple slides on it just because there was so much investment in this release. And because regex ends up being really important. If you look at APIs of .NET, there's a website that allows you to search all the APIs in .NET. There's some information there about how popular we see various APIs being. And one of the places that comes from is there's this API port tool that helps people migrating from .NET Framework to .NET Core understand what APIs they're using may not be available when they're targeting .NET Core. And that information is all aggregated into sort of give a general sense of how common various types and methods are and APIs in general within the framework. And from that, we can see that regex, according to this one stat, is used by about 65% of all the applications and services that were run through this tool. So a pretty high percentage. Similarly, just as another data point, if you search GitHub for system text regular expressions, you end up with about 1.7 million results. This stuff is used really heavily. Unfortunately, our level of investment in the past in regular expressions hasn't gone along with that. It's had seen very little change since .NET Framework 1.1, about 15 years. So for .NET 5, given how often this is being used, how frequently saw it showing up in profiles, and some competitive benchmarks that we saw popping up around the performance of regex and how we really needed to get .NET back to a competitive space, there were tons of improvements that went into .NET 5 for regular expressions. There's a whole blog post dedicated to this if you want to read more. But I do want to just give one example of the kind of optimizations that were done. Just I can't go through everything, just a subset. So one example, let's take this silly regex. What this is doing is it's basically saying that the expression must start with either this or this. Here, it can start with either an A or a B, followed by a CD, or it can start with an EF, followed by a G, H, or I. And then all of that must be followed by J, K, L, or M. If we look at the code that was generated for this in .NET Framework and .NET Core 3.1 and earlier, it's basically a loop. This find first char function, I'll take a step back. The regular expression engine is sort of divided into two pieces. The first piece is a method called find first char, and the second piece is a method called go. Find first char is all about blazing through the input as fast as it possibly can to find the first place that could possibly match the regular expression. And then once such a place has been found, it's then handed off to this go function that tries to run the full match expression at the location. And so our goal is that find first char can, as quickly as possible, get to the first possible place for a match, and also have as few false positives as possible. But if you look at the implementation that was generated on .NET Framework or .NET Core 3.1, you can see it's basically a loop that character by character through the input string is calling this char in class function. This char in class function is past the character that we're examining, as well as an internal representation of the things that we're looking for, and in this of the character class. And in this case, the engine has generated a character class for anything that could possibly start the string. So what could start this? What could start a match? Well, over here it could start with an A or a B, and over here it could start with an E. So the only possible things that could start a match are A, B, or E. This is an internal representation of that. And so every time we're calling char in class, we're passing that representation and the character to this function. That's not particularly fast, especially since this function ends up doing a binary search through the data that's presented in this internal representation. If you look at what we're doing now in .NET 5, there are a variety of things to notice. This sort of represents a few optimizations that kick in. The first is you'll notice this check up here at the top, this -7. What that's doing is factoring in the length of the input against what we've discovered to be the minimum length of any possible match. So for example, you can see that any match has to end with JKLM, and any match has to begin with either AB followed by CD, 3 characters, or EF followed by GH or I, again 3 characters, which means for something to match, it has to be at least 7 characters long. And so if you pass an input that is not 7 characters long, is less than that, we instantly bail out. Next, you'll see that rather than doing this character by character thing, we're actually able to take advantage of an internally vectorized function, index of any, which also highlights that any improvements made to index of any, like the one we saw on the previous slides, automatically accrues to regex and just makes regex that much faster. So the implementation recognized we're only looking for 3 characters. We have an overload of index of any that takes 3 characters. And so we can use this vectorized index of any to very quickly find a place where it might be A, B, or E. But on top of that, because A, B, and E are pretty common letters, the implementation then goes a step further and says, okay, well, not only must the first character be A, B, or E, but the second character has to be either a C or an F. And so it does a very quick check in the generated code for either C or F. And then on top of that, again, because we want to minimize false positives, it looks at the third character. It sees the third character must be either a D or a G or an H or an I. Now, based on some heuristics, it then decides checking for 4 characters is going to take too long. Instead, it generates a bitmap with 1 bit per ASCII character. And it quickly checks, is the input ASCII? And if it is ASCII, is it with some bit twiddling and masking, is it a 1 or a 0 at that location? Is it one of the characters we care about? If yes, we're going to run our matching engine here. If not, we're not. So these are the kinds of optimizations that were added into regex in this release. There are, again, many more. You can read the blog post to learn about them, but all of these combined lead to some pretty massive improvements. So rather than using a benchmark that I crafted, I've grabbed some benchmarks that are on GitHub that compare C# with Dart, with Go, with Rust, with C++, lots of different languages and frameworks being used. And I've just ported those exact patterns to use benchmark.net, and I'm also using the exact input that was being used on that site. And if I run this on .NET Framework, .NET Core 3.1, and .NET 5, we see something pretty impactful. From .NET Framework to .NET Core 3.1, there's not a whole lot of change, right? And I mentioned earlier that not a whole lot of investment had gone into .NET, into regular expressions until now. But if you look at .NET 5, you see massive improvements, about 20x faster, about 20x faster, about 10x faster. And these are sort of real world regular expressions that we expect to see out in the open. So some pretty significant improvements in regular expressions, which again, often make up a significant part of time in real applications. So it's exciting to see these kinds of improvements make their way in. Okay, then we're off to networking. And don't worry about all the links on this slide. I've just done this to kind of exemplify how many PRs have gone into improving the networking stack, and in particular on Linux in this release. It can be hard to demonstrate locally with just a loopback server or something, performance improvements in networking. So instead, I just want to show some examples from Tech Empower. So Tech Empower is a company, a consulting company, but they also run, they have these benchmarks that they've established, and lots of language and frameworks have submitted entries here against the multitude of benchmarks that are there to see how the various stacks rank up. And then we've used that when we're building ASP.NET Core and .NET Core, .NET 5 to kind of use as one goalpost for where and how we do optimizations. In the past, we focused very much with ASP.NET on the plain text benchmark, which is basically the simplest benchmark that's up there. And as you can see, ASP.NET is basically neck and neck with the best of the best up on this particular benchmark. But we haven't invested as much in some of these other benchmarks. And so for this release, we chose 2 more, one called JSON serialization, which does do some serialization and deserialization of JSON payloads, but it's really a benchmark for how fast you can read and write to the network. And then there's this Fortunes benchmark, which is about also not only how fast you can read and write to the network and do a little bit about a processing, but also how fast you can access a database behind the scenes. And there was a ton of work from folks on the .NET team, from folks at Red Hat, from community members like Ben Adams, to really improve the networking stack, and in particular on Linux, with an eye towards these benchmarks, which we also expect to accrue to a whole bunch of other workloads to make them go much faster. And this meant changes in sockets, this meant changes in system IO pipelines, changes in system text JSON, changes in the database provider that's being used to access the database, changes in ASP.NET and Kestrel, up and down the stack. And the results are pretty awesome. So I pulled from the website, the Tech and Power website, the official results from the last round 19, which was based on .NET Core 3.1. And then I pulled results from earlier this week that are based on .NET 5. And here you can see the ASP.NET Core entry on JSON serialization at about 900,000 requests per second, and with .NET 5 at about 1.22 million requests per second, also jumping up in the rankings from about 70 to about 34. So pretty cool results there. And then similarly on the Fortunes benchmark, there are a couple entries here, one of which is using just system.NET sockets, and one of which is using a different ASP.NET networking provider. But they're basically neck and neck at about 280,000 requests per second on .NET Core 3.1, and on .NET 5, we can see it at about 400,000 requests per second, jumping up from 26th position to the 9th position. So again, really cool results, and we're really hopeful that these will translate into significant wins for for arbitrary web services applications out there in the wild as well. I will do one benchmark that I did run locally, just because it's not represented by Tech and Power, but it is becoming more and more important, and that is HTTP 2. So in .NET Core 3.1, on both client and server, we did have an HTTP 2 implementation, but it wasn't particularly optimized. It was sort of our initial functionally correct foray into the space. But we spent a lot of time in .NET 5 optimizing it further, with an eye not only towards HTTP 2 directly, but also towards gRPC, which layers on top of it. There's now a gRPC provider implemented entirely in C# rather than one that's just a wrapper for C APIs. And James Newton King has done a lot of great work improving that library and making it really, really competitive. But that is also based on top of significant improvements in both the client and server stacks in .NET 5. So here I've got a simple, about as simple as you can get with an ASP.NET Core server. And all it's doing is for any GET request, it's spitting out hello in the response. And then I've got a benchmark.NET client that is making 50,000 HTTP2 GET requests to that endpoint per iteration of the benchmark. Basically 100 concurrent streams, each making 500 HTTP2 requests. And if we look at how long this takes, on .NET Core 3.1, we can see that these 50,000 calls took about 2,300 milliseconds. But on .NET 5, it's about 3x as fast, taking about 850 milliseconds, also using half the allocation. So again, really significant improvements, and we're pretty optimistic that these kinds of changes, especially for folks using gRPC, are going to result in some pretty massive improvements in their services, which is awesome. So with that, I will wrap things up and we can go to questions. I just wanted to call out one thing in particular, and that is I've talked about just a smattering of examples here, and I mentioned there were about 250 called out in this blog post on .NET 5 performance. About 20% of those actually came from folks outside of Microsoft, members of the .NET community that had a particular interest in seeing something improved. They went and submitted a PR. We worked with them and we got it in. And while I can't guarantee that any PR you submit will be merged, there's a very high likelihood it will, or at least we'll all learn something as part of the experience, and we try and be very welcoming for folks submitting PRs. So if there's something you'd like to see improved for .NET 6, I would highly encourage you to come to the .NET Runtime repo or the .NET ASP.NET Core repo, or whatever repo contains the code that you care a lot about, and work with us to make the thing faster, because we're really excited to do so. So with that, I think we should open it up to questions, and I've got time. We can take as much time as folks have questions for.
Awesome. Thank you for an awesome talk, and a meaty one with a lot of interesting, very interesting stuff. Yes, we have some questions. I hope more will come. So let's just start with the very first one, which is, it was when you started to show benchmarks comparing .NET 4.8 with the .NET 5, but I believe you pretty often also showed the comparison to .NET Core 3.1. So
yeah, I mean, I wanted to keep .NET Framework there as well, because there are still a significant number of applications that are migrating from .NET Framework to .NET Core, and that gap in many areas is, really impactful. So I wanted to highlight that. But the main purpose, I did want to show moving from .NET Core 3.1 to .NET 5, and so that's why all the benchmarks included that. The .NET Framework aspect is also why I ran all these examples on Windows. Because I wanted to be able to do the .NET Framework comparison apples to apples as well. But it's worth noting that I've also run all of these on Linux, and the gaps are similar. So the improvements aren't just Windows specific, or they're not just Linux specific, they're not just Mac OS specific. While some of the changes are specific to, some of those 250 PRs I call out are specific. In general, they're usually optimizations on Linux or on Mac OS that are trying to fill some gaps we had in the past between Linux and Windows. But anyhow, that's why I ran them all with Framework and Core 3.1 and 5.0.
Okay, awesome. Another question. Any plans adding read-only sequence to new APIs?
So there are not only plans to add read-only sequence to APIs, it's already been done in .NET 5 in many situations. You'll notice on the encoding class, for example, there are APIs overloads in addition to taking spans, taking read-only sequence. So yeah, and if there are others you feel are missing, please go and open issues in the .NET Runtime repo proposing them for .NET 6.
Absolutely great. Now we are talking about .NET 6. Okay, another question, an example when you showed the sorting example regarding the...
So why did I use as span.copy2 instead of array.copy2? No reason. I wrote it. I'm so used to typing it out. I probably just did it by accident. It's also possible I was copying it from something where there was a reason, but it doesn't matter. And that also wasn't the key thing being measured. So sorry.
Thank you, Kevin, for pointing that out. You have this finger memory to use span as many.
I do. It just comes out. Yeah.
Okay, next question. Pretty nice question. Where there are scenarios when this attribute can hurt performance, not.
So it shouldn't ever hurt performance. It's not guaranteed to help performance. It's pretty much just potentially eliminating some work that would have otherwise been done. I mean, the only way I could see it possibly hurting performance is if there was some kind of weird alignment issue with, the extra few and zeroing instructions caused the generated code to align in a different way, and that caused it to, some weird interaction with the hardware. But in general, no. What it does do, and the reason it's just not there by default, is it can impact functionality, and in particular around interop. So if, for example, you had a pinvoke or DLL import, and you passed and you declared in your signature, you had let's say an out int foo. The C# compiler isn't going to require you to have initialized the int that you pass as the out there, because it's expecting that the called method will initialize it. But because it's a DLL import, that's actually not guaranteed. You could call into a native function that's a no-op and doesn't actually write to that output. And as a result, with safe C# with that skip locals and init specified, you might actually seeing that out parameter containing whatever garbage was on the stack in that integer. And that's why skip locals and init actually requires you to specify to the C# compiler you want to allow unsafe code, because it kind of has, in some ways, the equivalent impact. So it could have a functional impact, so you should absolutely audit any code with which you decide to use skip locals and init. And we did that. We rolled it out slowly through the core libraries before we flipped the switch and did it everywhere. And also ensure you have really good test cases before you apply it. But no, it shouldn't hurt perf. And
as far as I remember, you can apply it not only on the methods, but only on the class level, on the module level, right?
You can apply it on all levels, yeah.
So
from the individual member up through the module.
So you are saying this is a current default, like always keep init and...
No, but it is a good tool to have in your tool belt.
Yeah, sure, sure. And just to clear it out, so there are no limitations. Like you can have references on the stack, you can stack alloc, you can not stack alloc. Any method can have this attribute, right?
Any method can have it. The runtime will still zero out things that it needs to zero out.
Awesome. It is aligned, and we know what parts of the stack should be
Yeah,
zeroed, what can be omitted.
Runtime may choose to ignore it if it had to zero everything, or if it was just in its best interest to zero everything, but it allows it to not do so.
Awesome. Okay. Another question is about 2.1 versus 3.1.
So I don't in these slides, but if you search for my last name, Toub, performance .NET Core 3.0, you'll find a blog post comparing basically the kinds of things we just walked through, going from .NET Core 2.1 to .NET Core 3.0. And similarly, hundreds upon hundreds of PRs called out with lots of examples. I don't have a blog post about .NET Core 3.1 because it was a very minor release from the core libraries and runtime perspective. It's basically, with the exception of some important bug fixes, there wasn't a whole lot of performance improvements in the core libraries between .NET Core 3.0 and .NET Core 3.1. So I didn't do a blog post because there wasn't that much to talk about. We did end up backporting from .NET 5 to .NET Core 3.1 some really impactful changes, especially in the JSON, system text JSON. There were some pretty big improvements there, which I didn't call out here because they're also available now in .NET Core 3.1 because we did backport them into a servicing release. So those aren't talked about, but you'll get most of the benefit from reading the .NET Core 3.0 perf blog post.
Awesome. Okay, we have a question about async, which is always valid, which is mostly, I will show you a few parts of it. So just this is the first part, and then it is a part whether we should in general call, maybe I will just rephrase it. If you have two.
Yeah, if I have two things I want to await, I want to await A and I want to await B. Is it better to do await A and then await B, or is it better to do await task.winAll AB?
Exactly.
In general, it's better to do await task.winAll AB from a performance perspective. Functionally, there might be situations where you want to do await A and then await B, but those are pretty rare. In general, you want to use the winAll. And the reason for that is, while winAll does incur an allocation for the task that it returns, it's also able to avoid re-entering all of your async machinery, calling back through synchronization context, and all that kind of stuff per task. It can just do it once, and the completion of a task basically just is an interlocked increment on the thing that the await.winAll is, the task.winAll is representing. So in general, it's better to use winAll. But you can also, if you're really concerned about it or really interested in it, you can always benchmark it yourself and choose whichever ends up being better for your scenario.
Sure, you have always benchmark.net in hand.
Yeah, I love benchmark.net. It's great. It's unfortunately it's not great for talks because it takes a while to give you valid results.
Yeah.
So that's why I have all the screenshots. But it's awesome.
Sometimes some folks are using this trickery, that magic that they are starting benchmark, but they have already prepared the results on the different tabs, so they are, and then they have just the result.
Exactly, and sometimes if I really want to show a demo running, I'll fall back to the simple stopwatch around a loop just to kind of show something, and then I get criticism. Why aren't you using benchmark.net? Which I totally get. It's just for presentation reasons.
Sure. Okay, next question. What books do you recommend to learn about writing optimal performance C# code?
I've heard there's a pretty good book on the GC and memory management. Conrad might know something about that.
Yeah, something I heard about it also.
I mean, for me, I used to read a lot of books. I have a hard time now sitting down and finding the time cover to cover to read a book. I find that blogs and things that I find on Twitter or wherever end up leading me to read much more manageable snippets. I also For me personally, I get a lot more benefit out of trying things, looking at them in the debugger, looking at them in a profiler, looking at them with benchmark.net, and just seeing what things cost and then digging into why. So kind of a more hands-on learning. But if you are interested in books, if you just search for C# and performance and book, or on Amazon or wherever, there are lots of books and they're all pretty good. At least kind of giving you the rough sense of the kinds of things to pay attention to. There's also some wonderful blog posts written by various folks over the years on the dev blog site, on Microsoft's dev blog site, by Vance Morrison, and so on, that are worth searching and reading.
I believe we can agree on some list and post it as a comment after the talk, or tomorrow, or just watch the recording, the recording on YouTube, and after some time we will just add a list of proposed materials or something like that.
Great.
Okay, and then there are some notes here, and then the next question. Yeah.
At some point, I wouldn't be surprised, but I don't believe we have AVX 512 support in the plans for .NET 6. I could be wrong, but I haven't seen any work towards that end. I think there might be some issues in the .NET Runtime repo related to it, so you can go and search. And if you don't find one, feel free to open one, and it's worth a discussion.
Right. Okay. Another questions regarding 2.1 versus 3.1. So I believe we have already covered that. So let's move to another. Let's just make sure I didn't skip anything. Okay. Okay.
Okay, so the question is basically on Windows. We've got this sort of pervasive mechanism in the OS called overlapped I/O, and it's how we implement async functionality at the sort of leaf levels. We utilize these async operations provided by the runtime, where basically we get to give as implemented by the OS, where basically we get to give a call back to the OS, and it will call back to us when the operation has completed. Overlapped I/O doesn't exist on Linux or Mac OS. It's a Windows-specific thing. What does exist on these other operating systems, however, is usually, so there are APIs like select and poll in POSIX that allow you to wait on multiple things at the same time. The problem with select and poll is that they don't scale very well, and it can be costly to use, especially as you have lots of operations starting and stopping. But both Linux and Mac and other Unix operating systems usually have some scalable version of that. So for example, we have epoll on Linux and we have KQ on Mac OS. And what these do is provide an OS-provided mechanism for registering file descriptors that you want to be monitored, and then being able to wait on one thing for any of those registered file descriptors to have something ready for you to process. And this scales really well. You can have one epoll with 10,000 file descriptors associated with it, or 100,000 file descriptors associated with it. And so if you look at something like system.net sockets on Linux, we use epoll. And when you create a new socket, we have basically one epoll. We have one dedicated thread for monitoring, basically in a loop, waiting on that epoll file descriptor. And then when sockets come along, you say new socket, we basically register that socket's file descriptor with that epoll. And then that one thread is just monitoring and waiting in a loop. And when it gets a notification from epoll that there's work to be done, it usually comes in a big batch. And then we can fire off work items to process each of those work items in that batch. And in fact, we significantly improved that mechanism in .NET 5. That's where a lot of the improvements came from in the TechEmpower JSON serialization benchmark, for example. We basically went from having multiple epolls to effectively generally a single epoll, and we improved how the work gets from there into the thread pool and how it scales across the thread pool, using techniques that are possible publicly, but just being more thoughtful about it. And that's basically how async I/O is achieved on Linux. And on Mac OS, it's the same thing, just using KQ instead of using epoll.
Awesome. Thank you for a great explanation. But as far as I know, I also remember this tweet from David that you are considering using this more modern AO on Linux, like Uring or something like that, that you are looking at all those new things coming
Yep,
to.
there's a technology called IOU ring that allows you to do more in user mode than you can do in kernel mode, and some initial benchmarks for it are pretty promising. Netty even recently has been publicizing some work they've been doing on Java to take advantage of this and showing some pretty promising results. However, getting those kinds of results with C#, we've done some prototyping of it, but really getting the benefits requires very, very, very new Linux kernels that aren't in any wide deployment yet. So we will definitely be looking at incorporating that in the future, but we haven't for .NET 5. It's just not pervasive enough to be meaningful yet.
Sure, not yet. And this transport that you mentioned, even in the context of Techem benchmarks, are using this different transport, right? The transport also trying to use another API as far as I remember.
Yeah, so the ASP.NET has sort of two prominent transports. I mean, it has a pluggable model, so you can put any networking thing you wanted underneath. But the most common one used is the one that's based on systemnet sockets, and it's the default. It also had one that was based on libuv, and then Red Hat published one that also plugged in, and that was one of the ones that was showing up in the benchmarks. If I go back, this was the one that was using Red Hat's this top line, and this is the one that was using systemnet sockets.
Yep.
And then over here, this is the one that was using Red Hat's, and so was this. The Red Hat one, basically, effectively, it creates kind of one epoll per processor, per core, and it tries to then keep all the work on the thread rather than queuing it off to the thread pool. It tries to keep all the work on that one dedicated thread to avoid these thread hops, try and make better use of caches and things like that. The trouble with this approach is it can be really good for perf. The trouble with this is if something were to block that process, that thread, it ends up blocking all other socket operations on any other socket associated with that epoll. So you can hang your system. If anyone has a blocking operation somewhere, you can either introduce significant delays or actually cause the whole thing to come to a grinding halt. We do actually, and I mentioned this in the .NET 5 blog post, we do have an experimental mode you can opt into in .NET 5. You can play with basically causing systemnet sockets to move into a system just like that, where it basically has one epoll per core and a dedicated thread, and it doesn't queue any work off. If you want to try it, and we're interested in understanding if that model does end up being beneficial for particular workloads. But again, it comes with some really, really dangerous possible results. You have to be very careful with it.
Sure. So it is nice for benchmarks, but it is pretty dangerous to be a totally default, let's say, solution.
Right.
I posted the link to this repo about the Linux transport published by Red Hat, and also you can refer to article mentioned by Steven and experiment with this mode, which probably will be also interesting for you to see the outcome. Okay, let's see the next questions. We have Adam online, so Adam is probably asking.
I work with Adam on a daily basis, so.
Yeah, no.
My one wish, he probably already knows, and so does the team working on it in Visual Studio. But right now, Visual Studio has some nice profilers built into it. One for doing kind of CPU investigations, and one for seeing all the allocations in your program and being able to track down where they're coming from. But that latter one currently only works on Windows. And I am excited for it to eventually work on Linux too. So that's my current desire right now, is to be able to use that tool on Linux.
Oh, so you know Adam already, so it's everything up to you. Okay, next question. It was exactly the same like we covered it. And next one.
To wrap a socket I connection in a pipe directly without using a network stream. I don't entirely understand the question. I think it's so. Oh,
I believe how you can
so
expose socket as a pipe.
So in system I/O pipelines, there's pipe readers and pipe writers, and there are APIs on there for creating pipe readers and pipe writers around streams. And I think the question is there an API for creating a pipe reader and writer directly on top of a socket instead of going through network stream? Not currently in .NET 5. I'm also not aware of any plans to create one. If memory serves, ASP.NET's implementation of their default provider effectively does that, but I'd have to double check. And so you could probably either use the code from ASP.NET Core or build something simple based on it. I'd be interested in seeing if there's any meaningful improvements as a result. Network stream ends up being a pretty thin wrapper. It basically flows right into the socket, and in fact, the optimizations in socket around things like value task, network stream is just returning, out of network stream's read async, it's just returning the exact same value task it gets out of socket.receive, receive async rather. So that it's a pretty thin layer, but I'd be interested in seeing what a direct mapping provided. That said, you often end up not wanting to go directly to the underlying connection, but there are often some transforms in the middle. So for example, a lot of connections these days are HTTPS. If you're using gRPC, by default, or you're using HTTP2, like you're using an SSL connection or TLS connection. And so there's going to be an SSL stream in the middle there. And that's a lot harder to employ, kind of going directly to the socket.
Awesome, thank you. Now we are switching to more high-level stuff, like we have Entity Framework Core, and any differences here in performance, memory management?
So I haven't, I was talking most about the lower levels, but as many improvements as you see going into the .NET kind of core libraries, there are also tons and tons of improvements going into ASP.NET Core, Windows Forms, Entity Framework, and so on. Some of the improvements that I demonstrated as part of the Tech Empower benchmarks. So I mentioned there were lots of improvements that went into a database provider. That was, a provider basically available via EF Core. So and Shai Rajansky did a lot of that work. So I encourage you to check that out. But yeah, there's definitely, and I think some of the release blog posts about .NET 5 are mentioned, like in each of the preview releases or in the RC release, mentioned improvements that have gone into EF. And then I think there have been a couple dedicated EF blog posts on the .NET blog site about improvements that have gone in, both functional and perf. So I'd encourage you to check that out.
Thank you. Next question regarding Linux.
Linux. So I'm not entirely sure where or how or what's been observed, but if there's a particular benchmark that you're concerned about, please feel free to open an issue in .NET Runtime and we can dig into it. I wouldn't expect the thread pool, for example, to be any slower on Linux than it is on Windows. There are some functional differences. For example, the thread pool has kind of two thread pools in it. It's got the what we typically think of the thread pool that you queues or work item into, and then there's this I/O pool underneath that's built on top of overlapped I/O on Windows. And since that overlapped I/O implementation doesn't exist on Linux, anything that's queued there just actually maps back to effectively queues or work item. And we are aware of, we would like to improve that. We're not entirely sure what to do there. There are some open issues related to that. So if that's what you're talking about, yeah, that's something we're looking into. But in terms of general multi-threading, I'm not aware of any significant deficiencies, but I'd like to understand more if you have some examples.
Yeah, so David, feel free to ping Steven on GitHub, for example, because as we know on Twitter, he's only observing, not tweeting.
Long time reader, time caller, yeah.
Exactly. And by the way, what's the status of the thread pool implementation? As far as I remember, there was a plan to rewrite it completely to C# also.
Yeah. So there's sort of was historically there's been a managed piece to the thread pool and there's been a native piece to the thread pool. We have a managed implementation of that native piece. That managed implementation is actually being used with Mono. When you run on Mono, you get the managed implementation rather than the native. We didn't quite get it in to be the default implementation on core CLR as well, but the plan is to do that in the future.
So .NET 6 or further?
I would hope .NET 6, but I can't make any guarantees.
Sure. Okay, this seems pretty low level, so maybe you will be able to answer.
Yes, so the question is, I'm going to generalize it. And I think the question is, if I get multiple packets on the network, might I get those in a single epoll wait involving a single kernel transition? Whether there's a single kernel transition would be up to the epoll implementation, but in general, the answer is yes. So yeah, whether it's TCP or UDP, you can wake up with multiple pieces of data potentially as part of a single operation. I don't understand the also completion ports part of the question.
Okay, so Alexander, if you are still here, you can follow up with an additional question, and then let's move on to something mentioning Nginx. So,
so the question is about reverse proxies and whether to have one in front of your Kestrel web server. So historically, we haven't recommended Kestrel be used sort of on the edge. We changed that a release or two ago, and now we say it's totally supported to be on the edge. So yeah, I would check that out. If you are interested in a reverse proxy for other reasons, there's also one that's being built. It's called YARP, and it's built entirely on ASP.NET. So I would check that out as well.
Great. A little bit of nice words, not a question. Just like.
You're very welcome. On behalf of everyone who did that work, and I don't believe this was me, you're very welcome. And I think there were, into this work in particular, I think there was contributions from the community as well. So, you know, yay, everyone. Good job.
So, good job, exactly.
Hi, Tanner. What is the best way to keep up to date with available optimizations and newer best practices? That's a great question. I would start with blog posts that get written by the likes of someone named Tanner Gooding, maybe, and me and other folks. Yeah, you know, every release we try and sort of evangelize the work that's been done in that release. We do so on GitHub. We do so in blog posts. When the next round of books get written, they try and factor that stuff in. So I would say, you know, to start, the best place is probably just subscribing to the .NET blog and seeing what comes out. Or even better, you know, participate in the .NET Runtime repo and pay attention to all the PRs that are going in. It can be pretty voluminous, so that can be hard. Or go talk to someone named Tanner, who, if you're looking for someone who knows hardware intrinsics inside and out, Tanner, go talk to yourself.
Yeah, and if anyone is else thinking about it, I can only add Twitter as a source. Although Steven is not on Twitter, there is a lot of other folks. And if someone has so many time that it can read Twitter, there are a lot of very nice up-to-date discussions all the day. So you can follow Ben Adams, for example, and you'll have a full day of interesting articles.
Definitely. I'd also add to that, at the beginning of the talk, I talked about some of the work being done in analyzers. And one of our hope with the analyzers is that we can sort of codify some of these best practices into rules that when you upgrade to the newer version of .NET, in addition to getting new APIs, you'll also get updated analyses that might help you determine where those would be useful or if best practices have changed. For example, towards one of the last things that I checked into .NET 5 was adding a new property to environment.processID. And this is meant to replace places where, if you search C# code, you'll find a lot of code doing process.getCurrentProcess.mainModule.name, which is a very expensive way of getting the current process, .id, of getting the current process ID. And so in addition to adding this API, at the same time, we also added a new analyzer, which looks for that pattern, process.getCurrentProcess.id, and recommends that you change it to use environment.processID, which is both simpler, more maintainable, and faster. So we try and when we added these new read async, write async overloads, we now have an analyzer that recommends you use them. There are new append and insert overloads on String Builder. We recommend you use those in certain situations. And so analyzers can kind of encode a lot of this stuff, not everything, but I think that's a pretty good way. You upgrade to the new SDK and more stuff lights up for you.
Great, great. And by the way, all those are they those analyzers open sourced? We can look at the.
They're all in the .NET Roslyn-analyzers repo.
Okay, and they are just a part of those. Oh, nice, yeah. Awesome. Another question is about gRPC code first approach.
I don't know the answer to that, but James Newton King would absolutely. So find him on Twitter or somewhere, and he can probably answer that for you off the top of his head.
Awesome. And the last question, while you can still ask some more questions, so we have a few minutes more.
I love this question. I want everyone to participate. So there are a variety of ways. Pick something that interests you. Pick an area that interests you. Go to, let's say it's in .NET Runtime. Go to the .NET Runtime repo, which encompasses core CLR, Mono, and basically all of the libraries that make up the core framework. Search issues, see if there's any issues that have been opened about things that people have expressed interest in. You might be able to pick off one that's marked easy or up for grabs, or you might examine the code in that function and see if there's anything that jumps out at you as something to improve. You might write an application that utilizes it and run it under a profiler and see if anything jumps out at you. A lot of the core functionality in the framework has been gone over with a fine-tooth comb and has been iterated on and iterated on and iterated on. So it might be hard to find things to improve there, just sort of fresh out of the gate. But if you focus on other areas higher up in the stack that may have received less attention but are still important to you, in many cases, I'm sure you'll be able to find something really quickly. Even if it's just an allocation here you could get rid of by switching from creating a string to using a span, or avoiding some unnecessary work that's being duplicated or some such thing. But I would say come to the repo, explore, and we will do our best to welcome you with open arms.
Great. I also feel invited. I will try to find something.
Yeah, everyone should. And if you ever feel like you're not welcome, please call us out on it. Sometimes it's just because we're, having a rough day and we're just being very, very fast in our typing, or maybe we meant to be friendly, but it didn't come across that way. So we definitely want people to contribute. We love it when people do, and we try and be very welcoming to it.
Yeah. And obviously, you shouldn't fear that you will explode anything. Like, you for sure review anything tremendously in a very tremendously detailed way. So don't be afraid of adding something. You will just validate it, right?
Yeah, and we might ask you to add tests to go along with it if we don't feel like we have sufficient coverage. We may end up having a discussion about it and decide the trade-offs involved, aren't the right ones for where we think we should be heading. Often optimizations involve making something faster in exchange for making something else slower. And so we'll have a conversation about, are those the right trade-offs based on kind of what we understand code using it to be. And at the end of the day, it may be that we decide collectively, this isn't the right thing, and we'll end up closing the PR. But more often than not, we try and find ways of merging PRs, and taking the hard work of everyone and getting the .NET community kind of en masse to be able to improve .NET.
Great. Okay. What do you think about source generators in terms of perf improvements?
That's a great question. So for anyone who doesn't know, source generators is a new feature of C# that kind of like analyzers are kind of plug into the compiler and are able to analyze the source code, where analyzers can then kind of flag certain pieces to say you might want to change this, and fixers can go in and change it. Source generators allow it to analyze the existing source code that's there and then generate additional source code that'll be included in that same compilation. And so you can use source code to do at compile time what you might have otherwise done using reflection and reflection emit to spit out some code. So I think source generators are awesome. So as one example I'd love to see us do, I don't know if we will, but I talked a little bit about regex earlier. And one of the ways there are multiple ways that regex can execute. The two main ways are it can interpret, given an input string, it can interpret the pattern over the input string, and basically for each instruction in the regex pattern, it can perform some operations. Or ahead of time, it can generate a compiled implementation dedicated to that pattern, and then for each input string, it just runs that code over the input. Today, that generation typically happens with reflection emit, which means that there is some overhead paid at startup time to generate that compiled code the first time you use it. That could absolutely be done with source generators because there's nothing that's really needed beyond the pattern as input. And it would allow you the code for that to be generated once and then just loaded rather than generated at runtime. Other examples of this would be things like JSON serialization. There's no reason we need to use reflection emit at runtime to generate a serializer and deserializer for JSON. We could do it with a source generator. And there are lots of opportunities like this. Anywhere you see reflection emit being used, there's a really good chance source generators could be used for that too. And in fact, if you look at the .NET Runtime lab repo, which is where some experiments related to .NET Runtime are happening, you'll see a few experiments in source generators there. There's an experiment going on with source generators for JSON serialization, like I just talked about. There's even one that's being done right now by some of the interop team, looking at using source generators for generating the marshalling stubs that are needed to be generated when talking from C# to C. Seeing if we can generate those with source generators rather than using the equivalent of reflection emit at runtime.
Right. This is something that probably Alexander was just following up, like using source generators for p-invoking something unmanaged.
Yeah, I don't know that. I'm not sure that source generators will make p-invokes easier. They could certainly make them faster in certain ways. Yeah. I'm not aware of any efforts to significantly improve the usability of DLL imports or p-invokes. But if you have something in mind, again, please feel free to open an issue in the .NET Runtime repo. We'd love to hear it.
Great. Kevin is just doing some kudos about your appearance on GitHub. So this is not a question. And I believe we are done with questions. I have only one left.
Thank you for the comment. I really appreciate it. I try and a lot of us try to be very welcoming. Sometimes I know I'm misinterpreted or I say something in a way that I didn't intend to say and it comes across wrong. And so I certainly apologize for any time that happens. But I'm glad that you found in general, me and us to be welcoming. We try really hard to be, and we really appreciate everyone's involvement and contributions.
Right. Non-verbal communication is always tricky. So, okay, I have one question. Just when were you showing this try to hex version improvement benchmark try to hex converting to hex? You showed pretty significant improvement from 3.1 to 5, but there was super significant improvement between .NET Framework and .NET Core 3.1 as far as I remember. I was just interested why. Do you know why this version is so much faster here?
I
Like,
haven't checked specifically in this example, but I can venture what I guess that I think is probably right, and that is there is the span that is built into .NET Core, but we
mhm.
released an out-of-band package for span that works with .NET Framework, which is what this would end up using on .NET Framework. It's a NuGet package that has its own implementation of span if you're on .NET Framework, and then it just type forwards to the span in .NET Core if you're on .NET Core. And there are optimizations that we can do with the span that's in .NET Core that we can't with the one that's on Framework. For example, the span that's available for .NET Framework isn't just a ref and an int. It's actually the underlying object. So it stores the array, for example, and the offset and the length. And that makes certain operations measurably slower. So for a benchmark like this, that's doing a lot of, and that's basically measuring how fast can we read and write into a span with a little bit of additional, math around it. Though those differences are probably getting magnified pretty significantly.
Okay, so this is the difference. Like we are using here span quite significantly many times, so it sums up to this noticeable difference, right?
Right.
Okay, we don't have any more questions, unfortunately, but we are almost 2 hours now, so maybe it is good time to indeed slowly end. Just the last words belong to Prashant, which is just saying that we should make such sessions more often, which I totally agree. So thank you for an awesome talk, even more awesome answers. And I hope we will see somewhere someday, maybe in face, if this COVID madness will end at some point in time.
Well, it's my pleasure. Thank you for having me.
Thank you for the talk. Thank you for attending this, for watching us, and let's meet somewhere online at least in the future. Have a nice day. Have a nice evening, depending when are you living. And bye. Thank you, Stephen.
Thank you.